Welcome to the learning curve. And this is another lesson that we are doing on hypothesis testing for single means. So here we are told that a manufacturer of sprinkler systems used for fire protection in office buildings claims that the true average system activation temperature is 140 degrees. So this is the claim that the true average system activation temperature is 140 degrees. So that's like the claim regarding the population mean, the established claim. A sample of 15 systems, when tested, yields a sample average activation temperature of 141 degrees. So that's the sample mean, and the sample size is 15. If the distribution of activation times is normal, so very importantly, we are told that the population is normally distributed with a standard deviation of 1.5. Does the data contradict the manufacturer's claim? At alpha, the level of significance equal 1%. So we're asked to state firstly here the null hypothesis and alternate hypothesis. So the null hypothesis, of course, would be H naught. So H naught here would be mu equal to the claim that is being challenged. And the claim that is being challenged here is that the average activation temperature is 140 degrees. So the established claim or the established information that is being challenged is the value that always goes in both the null and alternate hypothesis. So the null hypothesis here would be that mu, the mean, population mean, is equal to 140, while the alternate hypothesis, which represents a challenge to the null hypothesis, would be determined based on this final statement here that we're asked to explore. It says, does the data contradict the manufacturer's claim at alpha equals 1%? Since we're asked whether the data contradicts the claim that is made, that the average activation temperature is 140, then we will use a two-tailed test here, which is that mu is not equal to 140. Because does the data from the sample suggest basically that the mean activation temperature is different from that which is claimed by the manufacturer? Because we're asked to determine if it contradicts it, it's another way of saying, is there enough evidence to say that the average activation temperature is now different from what is claimed by the manufacturer? So when we have these kinds of situations, it's going to be a two-tailed test. And so that is why we use the not equal to sign in the alternate hypothesis. If it was a one-tailed test, we'd use greater than or less than, depending on the specific scenario in the question. Now we're asked to state the test statistic, of course, because this is a z-test. The test statistic is going to be z equal x bar minus mu divided by sigma upon the square root of n, where x bar represents the sample mean, mu represents the population mean, sigma represents the population standard deviation, and n is the sample size or number of observations. So we're not asked to do any calculation here in part B, merely to state the test statistic. That is the formula that we will use to come up with the calculated value. In step C here, we're asked to show the critical region graphically. So we draw our symmetric or normally distributed curve, or standard normal curve more specifically. And the standard normal curve is symmetric around the center value of 0. And what we're really going to do here is that we're going to mark our critical value, or critical values in this case, because it's a two-tailed test. We have to identify a critical value in both the right tail and left tail. And those values, to the left and right of those values, would be our critical or rejection region. To come up with that value, that critical value, which we will mark on both the right and left tail of the standard normal curve here, because it's a two-tailed test, we have to mark both tails. But if it was a one-tail test, like if it was a right-tail test, we would only mark the right tail, and if it was a left-tail test, we would only mark the left tail. But because it's a two-tail test, indicated by the fact that the null hypothesis has a not equal to sign, then we will have to mark both tails. So to come up with the critical value, we state the fact that alpha is equal to 1% as given to us in the question. Alpha, the level of significance is 1% or 0.01. That's what alpha is. And simply what we're going to do here is that we're going to subtract the value of alpha over 2. So because it's a two-tailed test, we have to divide alpha by 2. If you recall in my previous video on hypothesis testing, we did not divide alpha by 2 because we were doing a one-tail test, more specifically a right-tail test. When it's a one-tail test, you do not need to divide alpha by 2 before subtracting from 100%. So we'll divide alpha by 2 here, which is 1% divided by 2. When I divide 1% by 2, we get 0.5%. Then once you divide alpha by 2, our next step is to subtract 0.5 from 100%. 100% being the whole representing the curve, the entire area under the curve. So when we subtract 0.5% from 100%, we get 99.5%, or 99.5% expressed as a decimal would be 0.995. And this is the value that we will need to search for. This is the probability value that we will need to search for in the body of the standard normal curve, standard normal table. So I'll scroll down to the standard normal table here, and I'm going to be looking for in the body of the table the probability value of 0.995. When we find that value, we will read the z-score that corresponds to it, and that z-score will be our critical value. So let's look for 0.995, or the closest value to it. A reminder that as you go down and across in this standard normal table, the values get larger. So we're looking for 0.995, or the closest value to it. So 0.995, here we go through and we realize that the closest value to 0.99, so we have to be careful, it's 995. The closest value here to 0.995, the way to locate this value is to go to 0.99 here, and then you're trying to find 0.995 or the closest value to it. And here we have 0.9949 or 0.9951. And you could use the Z reading for any of these values and it would be fine, because both of them are equidistant from 0.9950. So I'm just going to use 0.9949, and the Z reading or critical reading that corresponds to 0.9949 would be 2.5. So we'll go down on the Z table until we reach the corresponding Z value for that probability, which is 2.5. And then we go up in that same column that the probability value is in to 0.07. So it therefore means that our Z reading or critical value would be 2.57. But if you had used 2.58, it would also be fine, because of the fact that this value 0.9951 is the same distance from 0.995 as 0.9949. So we're going to use our Z value of 2.57. So therefore, I'm going to write a statement here to say that therefore our Z alpha over 2 is equal to 2.57. This is our critical value. And I use Z alpha over 2 because of the fact that we divided alpha by 2 because it's a two-tailed test. So Z alpha over 2 is 2.57, or more specifically plus or minus 2.57, because it's a two-tailed test. So I'm going to go into the right tail here of the standard normal curve. I'm going to mark 2.57 at this point right here on the x-axis. This is one of the points here that will separate the rejection region from the non-rejection region. I also go into the left tail and I will mark this area right here as negative 2.57, and the area to the left of it will be our shaded area. Both of these areas will be our critical regions, or otherwise called our rejection regions. Right, so I have a rejection region to the left and a rejection region to the right, which will be the case when we have a two-tailed test. And the unshaded area is our non-rejection region. All right, and we will see how that is operationalized shortly. So this is my rejection region right there, both on the right and the left of the value here. The critical value to the right of 2.57 is rejection region, and to the left of negative 2.57 is also rejection region. So we'll come back to the curve shortly, but before we're asked to evaluate the test statistic. So to evaluate the test statistic here, Z is going to be equal to X bar minus mu divided by sigma over the square root of n. So basically we're using the test statistic formula to determine the calculated value. And you'll see the importance of that calculated value in a minute. X bar is the sample mean, and the sample mean given to us in the question is 141 degrees. So X bar, the sample mean, is 141. Mu will always come from the null hypothesis. That's the population mean of 140. And we're going to divide this. Let's just border this calculation that we did earlier off. We're going to divide this by sigma, the standard deviation, which is 1.5. And we're dividing that by the square root of 15n, which is the number of observations here, 15. So let's simplify this now. 141 minus 140 is going to be 1. And then now we're going to divide 1.5 here. We're going to divide 1.5 by the square root of 15. When we divide 1.5 by the square root of 15, we get 0.387. We could have rounded that to 2 decimal places, but of course, the more decimal places you use, the more accurate your results. So this is approximately 0.387. And then when we divide 1 by 0.387, we get 2.58. Rounded to 2 decimal places, our answer here is going to be 2.58. So now we have to ask ourselves the question, where in this standard normal curve, where on this standard normal curve that we have labeled would 2.58 fall? Well, 2.58 would fall slightly to the right of 2.57. Remember that 2.57 here begins the rejection region. So this region, as I indicated earlier, that is not shaded is the non-rejection region. So any calculated value that falls in the non-rejection region here would lead us to the conclusion of not rejecting the null hypothesis. So this is our non-rejection region. All of this area here is non-rejection, the unshaded region. But 2.58 is larger than 2.57, so it would fall in the rejection region here. 2.58 would fall in the rejection region because it's slightly larger than 2.57. So because 2.58, which is our test statistic value or calculated value, falls in the rejection region, then it means that we must reject the null hypothesis. If the calculated value here was a value like 1, then 1 would fall safely in the non-rejection region. But because 2.58 is slightly larger than 2.57, then it means that it is in the rejection region. So that will help us to answer the next question. Do we reject or fail to reject the null hypothesis and state our conclusion? Well, here we say we reject the null hypothesis. We reject the null hypothesis because the calculated value, or test statistic value, in other words, test statistic falls in the rejection region. The test statistic falls in the rejection region. In other words, once the absolute value of the test statistic is greater than the critical value, we reject the null hypothesis. So if we are rejecting the null hypothesis, it means that there is enough evidence to support the notion here that the data from the sample contradicts the manufacturer's claim at the 1% level of significance. So we reject the null hypothesis because the test statistic falls in the rejection region, and conclude that the data contradicts the manufacturer's claim. The data contradicts the manufacturer's claim at the 1% level of significance, which is the value of alpha. And that concludes this illustrative lesson on hypothesis testing for means. In particular, we looked at a two-tailed test problem this time around. I hope you found this to be a solid lesson in learning. Thank you very much for joining. Remember to like, subscribe, and stay tuned to the learning curve. Thank you, everyone.